All right, so I'm going to get started today. And also just anyone who has any questions come up, please put them in the question box. Leave them out for me. I'll go over them for a few minutes at the end of the presentation. So just getting started here, the topic of the webinar is Decoding the Machine Mind, the quest for explainability in machine learning. And so the goal here is to just get an understanding of how we can make use of explainability tools to really make our models better and also make them just better for the people who end up using them. So diving right into the overview here, I'm going to start by talking a little bit about just what explainability is, what I mean when I use that term. I'll go over some key concepts, and we'll talk about the idea of explanation scope. I'll dive into that a little more once we get to it. I'll talk just briefly about some explainer algorithms, and then we'll end with explainability for large language models. I know that's a topic of interest for a lot of people these days, so I wanted to get that into the presentation. So getting into what explainability is, I think I first want to just start by kind of motivating what we want it for. What is it that makes us want to understand more about models? So if we imagine for this scenario, kind of a particular machine learning model, let's say we're a bank and we're developing this model that is going to decide whether a mortgage application should be approved or not for the customers of the bank, right? So from the perspective of the customer, if they're getting an application that's denied, they might want to know why that application wasn't approved. And of course, the bank might want to be able to provide some kind of explanation for that, even if there is sort of an algorithmic element to that decision. Next, kind of from the perspective of a data scientist, somebody who might be a model owner or might have developed that model, they may want to know why the model isn't performing as well as they'd like to, why it's giving them too many false negatives maybe, or just understand what might be going wrong and kind of some support in that debugging process. And then finally, from the perspective of maybe a business leader, there might be concerns that a mortgage approval model should comply with transparency standards or privacy standards, or making sure that it's fair and not biased, generally just making sure that that model is performant in the way that it needs to be. So kind of given that motivation, I want to also kind of differentiate two concepts here, interpretability and explainability. So, the main idea here is we want to understand more about how models work, but there's kind of some different approaches to doing that. And so when we talk about interpretable models, we're really talking about models that are kind of naturally understandable without any additional aids or techniques. So these are things that as a model, I can kind of look at the inner workings of them and have a pretty intuitive understanding of what maps the inputs of the model to the output of the model. So this would sort of be models like linear models or decision trees that are relatively small. I'd be able to treat those as interpretable models, and I wouldn't really need any explanation techniques. Realistically, often in machine learning use cases, we have models that have to be much more complex than that. So we're not really able to use these types of interpretable models. And the models that we are using are just much too complex to really understand very intuitively as a human. And so that's where explainability comes in. We really have to rely on these specialized techniques or even additional models to make our model more comprehensible to the humans that are interacting with it. So really, when we get to that question, what is explainability? I'm just defining model explainability here as an approach to providing visibility into how complex machine learning models work. And I do want to also highlight here that explainability is really just one component of a much larger concept of model observability, which is really what Arthur is about, but it's about, everything from model and data documentation to any validation that's important, performance drift and uncertainty metrics, fairness and bias analyses, these deep inference level evaluations, and then of course also explainability or interpretability. So this is one part of that much bigger puzzle, and we'll kind of talk about that throughout the presentation. But the idea here is that it's not just explainability, right? It's kind of one piece of everything. So getting into some of the key ideas here. One thing that always comes up when you're talking about sort of explanations is what really makes an explainer algorithm or an explanation good? And it's a complicated question because there's really no single ground truth for an explanation. We don't have an objective truth to like whether that explanation was right or not. So that makes it a little tricky. So the way that people tend to approach it in this field is really to say that a good explanation is one that is understandable and useful to the end users. And so I like to kind of describe this as really as a human interacting with a machine learning system. I'm creating my own mental model of how that machine learning system works and what its limitations are and how much I can trust it and how I should use it. So the goal of explainability here is to just improve my mental model of that system, really just get me to understand it better in that intuitive sense. So kind of going on to that, like for explainers to be useful, they have to present explanations in a way that are comprehensible and intuitive to me so that I can improve my mental model. And I kind of went through and came up with a couple examples of how that can be done. And this is a really important part to explanations because it turns out that the kind of the raw outputs of explainer algorithms are just not that easily comprehensible to a person. Even though we see these algorithms that create explanations, we don't necessarily even easily understand those right at face value. So one of the ways to kind of make that easier is to use visualizations, right? Effectively summarizing numbers in ways that are visual and really sort of appealing to humans to understand. The next part of that is just interactivity. So a user interacting with a machine learning system will just engage more cognitively with that system, with that model, with that explanation, if it's kind of interactive, right? And it also promotes critical thinking. It helps us to kind of think hard about how our model's behaving, whether we should trust it, where we should trust it, kind of all those components. And then the last thing, like I mentioned just a bit earlier, is really including more of the model context. It's really important when you're interacting with a model and an explanation for a model to be aware of things like performance and drift when you're thinking about explanations. If a model's performing really, really badly, it's pretty likely the explanations aren't that useful either. So all of this is part of developing that holistic understanding of the model and how it works. And just to give some slightly more concrete examples of these, I just want to talk about how we sort of surface these explanations for different types of models and data. So for tabular, for example, we use feature importance plots, right? These are just sort of like bar plots that show the value, the amount that a particular feature contributes to the model's output in general. And one of the cool things that we can do is add some interactivity into that, where we might use this feature called what if, so where we can kind of change the values of particular features and see what happens to the model. Does that change the feature importance for that particular sample if we change different values? Does it change the way the model behaves? It gives us that experimental kind of approach to interacting with the model. And then, of course, for image or for text data, we can present explanations kind of by highlighting portions of that text or words with or portions of that image or words within that text that contribute significantly to the output that the model gives us. So getting into explanation scope. So this is kind of about how much of the model are we actually explaining with a particular explanation. So there's two ways to kind of look at this, global and local scope for explanations. For the global scope, this is really looking at whole model level explanation. So the idea is to give us a holistic view of why the model behaves the way it does. So one way to also look at this is actually regional explanations. Maybe I just want to look at particular segments of my data and how the model treats those segments or how that might differ. And this usually shows up as feature importance scores, kind of like I showed above, where we might look at how important each individual feature is to a model at a global scale. So some ways that we can put this into practice, really the idea here is that we want to understand the model as a whole, kind of in general. It might not necessarily always apply to specific samples, but this can give us kind of an understanding of generally how the model behaves. It can also kind of help us to look, if we look at global feature importance with the context of drift in mind, looking at how unexpected changes in feature importance might help us to highlight data drift. Or looking at global feature importance, we might be able to notice certain features that we might want to drop from the model during sort of a debugging process, or identify slices that might be features that might be contributing to fairness or bias issues. So there's a number of things that we can do with feature importance beyond just sort of generally helping us to understand the model. And so with this, I'm actually going to go into an example in the Arthur platform. So here, I'm just going to dive into one of our models. So this right here is the mortgage approval model. This is the same example that I gave at the top of the presentation. So this model is a very simple tabular binary classification model that is deciding whether or not a bank should approve a customer for a mortgage. So relatively simple model, and I'm going to skip most of the platform. Hopefully most of you have some familiarity with it already. If not, we've got plenty of other content for that. But For now, I'm just going to go into our global explanation section here. And so that's really this feature importance by PSI plot. When we're talking about PSI, that's actually a metric for data drift. You may already be familiar with this. So the way that Arthur actually approaches global feature importance is always in the context of PSI. We're able to look at that, at least on the UI, kind of in this format where we're looking at how it relates to drift. And as you can see on this plot here along the x-axis here, we are looking at data drift. So how much is the model drift as we go up the x-axis? And then we also are looking at feature importance going up the y-axis. So how significant is this feature globally to the model? So each of these dots here is one feature in our model, right? So the way we kind of look at this is first, maybe if we're interested in feature importances, which features are the highest up here? We've got a very obvious one, that debt to income ratio, very high. Now we do see this is a little bit high in that drift area as well. Now, for this particular model, I can tell you like these drift values of 0.0008 is very, very low. So even though this is like relatively high compared to these other features, it's a really low drift value. We're not too concerned about it. But it does tell us that like this fairly important feature to the model does tend to be a little bit more drifty so far relative to other features. So it might be something to track, maybe set some alerts on. But that's kind of the general idea of how we might look at feature importance, global feature importance with drift. Go back into the presentation here, and we'll move on to local explainability. So local explainability is really about single sample level explanations. The idea here is that we're making a hypothesis of why the model made the prediction that it did, given the particular inputs that it got. So this, again, is usually presented as feature importance scores, kind of like we saw for tabular models, but it can also be that highlighted text or images if we're looking at specific samples and want to see what parts of that image or what words in that text contributed to the prediction that the model made. And again, kind of how these come into use in practice with local explanations. It's a great way to gut check model behavior if you want to like pick out specific samples that you might be interested in seeing how the model treats those. Sometimes it is surprisingly different than the global feature importance, so that can be kind of interest. Another really useful tool or process here is troubleshooting anomalous samples. So if you've got some anomalous samples and you want to see why that model is treating those samples differently or how it's treating them differently, it's a really great way to compare anomalous samples to in-distribution data. And then there's just general model debugging, identifying top contributing features for the incorrectly predicted samples, trying to figure out why a model is getting certain features wrong can be really useful by just diving into some of those specific wrongly predicted examples. And again, I'm going to go back into Arthur to show what that looks like on the platform. So here we're just going to go into our inferences deep dive. And I do apologize. It looks like I was locked out of the system here. All right, back into the inferences deep dive. Sorry about that. And here we go. We'll just go into the first inference here. So this is an overview of our sort of individual inferences. Looking over here, we can get some general information about this inference. We can see that this was predicted positive. So the prediction the model made was that this application should be approved. But it was a false positive. So the model was incorrect on this one. It's not a very anomalous sample. It's relatively kind of standard. So it should be in distribution, but the model did get it wrong. So over here, we've got a list of all of the inputs here, all of the features that went into this model. And by shifting here, we can just see what contributed under these local feature importances, what feature contributed most to that prediction, that one prediction that the model made. Similar to our global explainability, we can see debt to income ratio is the most significant feature to this model. But let's try to play around and see if something changes here if we use this what if feature. So I'm going to try to see what happens if I change some of these values. We can see if the model changes anything. And we do see if I change this loan type from a 1 to a 2, that we actually got a pretty significant shift in the feature importances. Suddenly this loan type becomes much more important and debt to income ratio becomes less important. It didn't shift our actual prediction, but it did make some changes. I'm going to try to make one more change here and change the loan purpose. And we see that actually shifted things enough to flip the prediction. So if these two values had been different, we would have gotten a different prediction, actually the correct prediction on this particular sample. So very interesting way to kind of understand a model and play with it and get that intuitive sense of what's going on in it. There's a lot more to do here. And I think looking at more samples kind of can help as a data scientist to dig into what might be going wrong. But I'll get back into the presentation here just to move us along. And I'm going to get into a little bit explainer algorithms, just a very general overview for today. Definitely happy to answer more questions at the end. But overall at Arthur, we use two explainer algorithms called LIME and SHAP. And you may have some familiarity with these already. These are pretty industry standard, so a lot of people use these. LIME, local interpretable model agnostic explanation. So this type of algorithm creates this interpretable local model. So a really tiny model for every sample that it is trying to come up with an explanation for, using these perturbation methods to kind of test out different types of data or versions of the data and see how they perform on the model. So the idea here is to, again, explain the importance of each feature to the model output. And this is all aggregated then to create those global explanations. So both of these methods are really focused towards local explanations and then just aggregated to make the global explanation. SHAP is just a little bit different. It's fairly similar. This is Shapley additive explanations. You may also be familiar with these. This technique actually applies game theory to calculate the contribution of each feature to the final prediction. Overall, it's a fairly similar method, but there's a little bit of a different approach there. The benefit of SHAP is that it does take into account interactions between the features. And so that really leads to having a more stable explanation. So having kind of similar data points, you'll tend to get similar explanations with SHAP more so than with LIME. And then just overall, kind of how to decide which of these to use. At Arthur right now, we support SHAP only for tabular data, and we support LIME for tabular, computer vision, and natural language processing data. So there's a little bit of a restriction there. But generally for these algorithms, LIME is a lot faster. So if there's kind of constraints on time or on compute, LIME is a little bit better. But SHAP does provide those more stable explanations, which tend to be a little bit higher quality for a lot of people. So that tends to be preferred in those cases. All right. So the last bit here, I just want to talk a little bit of explainability for LLMs. It does get a little complex here because not that much research has been done yet. But I did want to dive into a little bit more, less on the academic side and more on how people want to use explainability for language models. And so I found a paper that was actually written a few years ago before kind of all this hype over the language models, before it kind of got to be a cool thing to do. But these people were looking at users that were interacting, that were programmers writing, software engineers writing code, and sort of these use cases for large language models that do code automation. So like auto completion, translating between programming languages, and then translating natural language to code. So these really useful kind of software engineering tasks, and trying to figure out, asking these users, these software engineers, how they might use explainability methods or want explainability methods to help them kind of make use of this large language model, right? So that was the idea here. And what the findings were, I'm going to give them fairly broadly here, but what they found was that overall, broader observability is needed beyond what is traditionally considered to be sort of an explainability technique. So for these large language models, the kind of standard explainability approach is using attention distributions. I won't get into the detail on that, but that's similar to what we talk about with kind of these LIME and SHAP, a little bit more in depth, getting into the weeds of the model. This is a typical sort of explanation, but a lot of the users of these that they tested in this study really wanted more in terms of documentation, wanting examples, tutorials, performance metrics on like how well these models do. They wanted to understand model uncertainty, and they wanted to be able to interact with the model and understand how uncertain it was for each line of code that it generated. And they wanted some social transparency. They wanted to understand who else was using that model and how they were using it, and whether they could learn how to use it better from other people. So there are a lot of other components to sort of this observability beyond what you would traditionally think of as explainability for models. And then going to the next part here, they also found that this was just highly context dependent, right? So these particular users were programmers, they were trying to use models to optimize code, but I think what might be useful for explanations could also vary quite a bit. For example, for those of us that are using ChatGPT to do some kind of broad language tasks. So like what we might require might be different, and there's just a lot more research to be done in that area. And then finally, actionability or utility-oriented understanding. The users of this particular type of model really just wanted to understand the model more and how it could help them to sort of accomplish the goal more than just kind of understanding like the weeds of how the model works. They wanted to know how it could help them, how much they should trust it, and like what would help them use that tool better. So that's kind of the overall. I think like my takeaway from this was that LLMs really highlight that broader need for context dependent and interactive explainability. And it also highlights that holistic observability and social transparency are really important, like looking at more than just the basic explanations and really just viewing kind of the whole picture of how a model is used. And so the very last thing I wanted to get into here is just how much we can really trust explainers, because I think this is a big question. This is something we need to be asking. Because really overall, these model explanations don't necessarily tell us much about like the causality of an underlying system that a model is about. They don't necessarily tell us all of the details of what's going on inside of a model. They really are just making these hypotheses about how the input data might map to the model output, right? And so the way I think of these, the way I find them to be useful is I kind of think of it as like the model is just this whole world, this hiking trail that I might be walking through in the mountains. And it's got all these details. There's a lot going on there. There might be, you know, a tree that's fallen on the path. There's a lot to kind of navigate. And I've got a map that's sort of representative of that path that I'm on, right? And so that map is representative, but it doesn't tell me everything. It's helping me to navigate that space. And I really think that explanations kind of are analogous to a map, right? They help us to navigate our models, but they don't necessarily tell us every detail that we might need to know. So the goal is to really just make those explanations better, right? Make them easier to use and more helpful. So that is what I'd like to leave you with. I will go ahead and answer any questions that have come up in the chat here. And feel free to add more. Okay, so the question I see here is which sectors do I think explainability is most important for? I think it varies. I've actually used explainability a lot in like scientific research, and I've heard a lot of like I've worked with a lot of people who've really made use of it in that area. So I think that's a big one. I do think like as we're looking at people doing these like code generation tools, through LLMs, I think like those types of explainability techniques will really be helpful in just helping people to be able to understand like where they can trust the model and where they can't. So those are the big ones. I know a lot of like customers and people I work with also make use of them in sort of these like highly regulated areas where they're expected to sort of have explanations for why decisions were made, like in banking. I think some of that depends on like what your regulatory space is like. The next one I see is, can I speak to the relationship between explainability and fairness? Yeah, I think that's a tricky one. I know like there are some cases where people will use explainability algorithms to decide like whether a model is fair or not. I do think it's better to like define specific fairness metrics and specific like groups that you want to track and kind of do that alongside explainability rather than like depending on explainability to tell you whether your model's fair or not. So like it can add information, but I guess personally I wouldn't want to just depend on explainability to like tell me that my model's fair. I'd want to kind of have my own like a separate system to do that as well. Next we have here, are there trade-offs between accuracy and explainability? And how are these managed? I think they're that's a little bit of a tricky question. I think when you're talking about like interpretability, for example, if you're trying to make a very simple interpretable model, there can be trade-offs. It really depends. Sometimes there aren't. Sometimes you can make a very interpretable, simple model that performs as well as you need it to. With explainability, not necessarily. Like the algorithms like Lyman Shap they work on, you know, they're model agnostic. They can work on any type of model. So you're not really losing anything in your, you know, in your ability to explain with those types of algorithms. But I would say like, you know, if your model's performing badly, right? If you have low accuracy, I would also be less trustful of explanation. So I think that's also the trade-off to consider. Like if your model's not doing well, I would be very like, yeah, hesitant about trusting any explanations that are given. I think that's the last one I've got. Any more before we wrap it up? All right. I'm not seeing any more questions. Thank you everyone for joining. And yeah, feel free to check out our documentation, Arthur, too, if you've got more questions related to this. We've got lots. Yeah, and we'll wrap it up here. Have a good rest of your afternoon.